All right, so while most jumps occur when we have piecewise function, there is another type of function that can create a jump that we want you to be aware of. And that's going to be a function where there's an absolute value involved within the fraction here. So basic example is f of x equals the absolute value of x over x. Now, imagine taking away that absolute value. You would have x over x, which would always just be 1. So if I think about just kind of creating a table of values here, if I think about plugging in a 1 into this, I'd have the absolute value of 1 over 1, which is just 1 over 1, which gives me 1. So at 1, I have a y value of 1. If I plug in 2, now I have the absolute value of 2 over 2. Well, that's just 2 over 2. That's 1. And if I do one more, I have absolute value of 3 over 3. That's going to just give me 1 as well. So it looks like right now that I would have some type of horizontal line. But what if I chose 0? Well, now I have the absolute value of 0 over 0. And the absolute value of 0 is 0, but I now have 0 over 0. Well, that is an issue. What do we do? 0 over 0. Is that 0? Is that not possible? What is that? Well, in this case, it is something that is undefined. You can't divide by 0 even if the numerator is 0. And so if it's undefined here, it turns out that I don't have a value right there when x is 0. And so what I get is anything where the x value is bigger than that is going to lead to just having a y value of 1. So I get a horizontal line right there, but it's undefined and therefore needs a hole at when x is 0. But what about if we have some values that are negative? So if I had negative 1 for my x, well, now I have the absolute value of negative 1 over negative 1, which is 1 over negative 1, which leads me to a value of negative 1. So now when x is negative 1, y is negative 1. If x were negative 2, I have the absolute value of negative 2 over negative 2, which is 2 over negative 2, and I get a value of negative 1 there. So it looks like now that if I have values of x that are negative and I keep getting smaller, those are also going to have a y value of 1. And so I get another horizontal line right here. But what happens as I get closer and closer to x being 0? Well, there's still 1 until I get to that 0, because if I plug in a value of x that's 0, once again I'm going to have a 0 in my denominator, and that makes that function undefined. So I have this step function here where I have two holes when x is 0, but then everywhere else the y values are either 1 or negative 1. Okay, so that's an example of another step function. So this leads us to kind of this dilemma of well, what happens if we have a 0 over 0? I think we're all pretty confident in saying that if we have anything divided by anything, that equals 1. So examples, 5 over 5, that's 1. Negative 8 over negative 8, 1. Bob over Bob, 1. But what about 0 over 0? That is not equal to 1. Okay, well, let's look at a second thing. 0 divided by anything equals 0. So 0 divided by 10 is 0. 0 divided by negative 50 is 0. 0 divided by pi would also be 0. Well, 0 divided by 0, what's that? Well, what we need to remember here is when we use the word anything, that 0 can't be the word anything. It works for other numbers, but 0 divided by 0 is not 0. 0 divided by 0 is not 1. Anytime we are dividing by 0, we have something that's undefined. And when we look at this graphically, this is where these discontinuities come into play. And we're going to look at basically some examples here of when dividing by 0 gives us a vertical asymptote and when it gives us a hole. Now, we're going to be talking about rational functions in more depth in the next couple days, but I wanted you to kind of think about these four kind of basic rational functions. We have f of x equals 1 over x, f of x equals 1 over x squared, f of x equals negative 1 over x squared, and f of x equals negative 1 over x. And I've drawn the four graphs of these to the right here, but what I'd like us to do is kind of think about which one matches with the others, or which equation matches with the graph. And this has to do, they all have a vertical asymptote at 0, and that's because in all these cases, if you plugged in a 0 for x, you'd have a denominator with 0, so it's undefined. So in this case, they're all vertical asymptotes. Well, what's happening on either side of the asymptotes? Well, if we consider this one, f of x equals 1 over x squared. Well, if I plug in any value for x, whether that value is positive or negative, we've already said it can't be 0, but if I plug in any positive or negative number, I'm going to get a denominator that's positive. So a positive x is going to result in a positive y. A negative x is also going to result in a positive y. And so it turns out here that this matches with this graph right here because the y values are always positive. Well, imagine the one below that, f of x equals negative 1 over x squared. Well, now the denominator once again will always be positive, but if I'm going to take negative 1 over something that's positive, now no matter what my x values are, positive or negative, my y values have to be negative. And so that would be represented by this graph here. So then our other two, 1 over x and negative 1 over x, on that top one, if x is positive, then we're going to have 1 over a positive, which is going to result in a positive. But if x is negative, then 1 over any negative will result in a negative. Well, this graph right here has positive x's associated with positive y's and negative x's associated with negative y's. And so that leads us then to having negative 1 over x matching with this graph here. So we're going to be talking a little bit more about the degree, or you might remember the term multiplicity from college algebra or from pre-cal. And the multiplicity that we're interested in specifically are the multiplicities, these exponent values in the denominator. So if you notice my evens, even exponents resulted in having the same direction, whereas my odd exponents resulted in opposite behavior happening at that asymptote. Okay? So you might also think of even as equal. So even, equal, odd, opposite. Okay? All right, so let's look at an example where we have a vertical asymptote. In this function right here, we have x squared plus 5x plus 7. You could try and factor that top part there, but it can't be factored. Now, even if it could, we would want to kind of compare it to what we have in the denominator here. In this case, since I don't have my denominator of x minus 4 being able to be simplified with anything from the numerator, I'm going to have some type of vertical asymptote when my denominator here equals 0. And so the value of x that causes my denominator to be 0 is x equaling 4. And so I know that in terms of my continuous function or values that I can have any value in this function except for 4 that will give me an output. So my x value cannot equal 4, meaning I'm going to have a vertical asymptote here at 4. Now, if I think about the behavior on either side of this, because this has a multiplicity basically of 1, if you were to put an exponent there, it would be 1. That means that on either side of this asymptote, we're going to have opposite behaviors, meaning on one side of it, it's going to go kind of up, and on the other side, it's going to go down. Well, how do we know which one is which? Well, what we could do is think about choosing something that's just a little bit bigger than 4. So maybe I choose like 4.1 as my x, and I plug it in. If I do that, hopefully you can see that my numerator here, I don't really care what the value is, but 4.1 squared plus 5 times 4.1 plus 7, that's going to give me a positive value. And 4.1 minus 4 in the denominator will also give me a positive value. So I know that if I'm just a little bit to the right of my asymptote here, my output is going to be a positive number, meaning that my curve here, as I get really close to that asymptote on the right side of it, when I had like 4.1, I'm going to have a positive value. Well, that means that on the left side of it, I'm going to have some type of asymptote, or some type of my curve, sorry, that's going down. Now, I don't know exactly what the rest of the curve looks like. It actually turns out that this this rational function has an oblique asymptote, and it kind of curves back up here and kind of curves back down there. We'll get into that a little bit more later, but what I want you to focus on here is this idea that I can figure out what's happening right here on either side of that asymptote, whether the curves are going up or down. And I know in this case, because of the multiplicity of that denominator's exponent, that they should be going in opposite directions. All right, so what about holes? On this one right here, I want to try and factor the numerator if possible, and I can factor out an x from it, and that leaves me with x times the quantity x minus 3 all over x minus 3. Well, this can be simplified. If I think about trying to reduce this, x over 3 over x minus 3 over x minus 3 really has a value of 1. And so what I have here is really x times 1, which just gives me x. Well, does that mean then that if I were to plug in f of x equaling x, or plug in this original function that I was given, would I have the same graph? Let's actually look at that on Desmos. So if I type in f of x equals x squared minus 3x over x minus 3, I get a line. And it's just a line, looks like, that goes through the origin and has a slope of 1. So if I type in g of x equals x, well, that sure looks like it's the same line. So are they indeed actually exactly the same? Well, the answer to that is no. And the reason why, and this is something that you have to be very careful of, you cannot say that f of x is equal to x. What you can say, though, is that f of x here is equal to x for all values except x cannot equal 3. Well, why can't x equal 3? X can't equal 3 because if I plug in a 3, I'm going to get a denominator of 0. Okay, so that whole denominator there will result in 0 if x is 3. So it's undefined right there. Okay, but it's not undefined because of an asymptote, it's undefined because of a hole. And I'm about to run out of time on this video, so I'm going to stop it here and we'll wrap things up here with a very short final video.